Hello everyone, welcome to the channel Statistica. So in previous lecture we are doing the concept of change of basis. Now we'll see that how the change of basis affects the coordinates of a vector in a vector space. Okay, so we are seeing uh, effect of change of basis on the coordinates of a vector. Okay, so let's just see it. Let's say I am considering the mapping as T of R cube to R cube. Okay, and I have the basis of this as S is my basis, which is U1, U2, U3, the corresponding vectors of this basis, and I have another basis which is S dash, and its vectors are V1, V2, V3. These are my bases. Okay, and there is a matrix P, which is my change of basis matrix from S to S dash. Okay, so we'll just find the P matrix first, and for finding that, we'll write every vector Vi in the linear combination of the Ui vectors. Okay, so for writing that, V1 equals to A1 U1 plus A2 U2 plus A3 U3. Similarly, V2 equals to B1 U1 plus B2 U2 plus B3 U3, and V3 equals to C1 U1 plus C2 U2 plus C3 U3. Okay, and where these AIs, BIs, and CIs are the belongs to the field of scalars. Okay, now I can write this system of equation in the y equals to AX form, and my corresponding A will be A1, A2, A3, and B1, B2, B3, C1, C2, C3. And the transpose of this matrix A will be my P, change of basis matrix, which is my P will be A1, A2, A3, B1, B2, B3, and C1, C2, C3. And you can also see it as, if I take the coordinate vectors of this vector V1, then there will be A1, A2, A3, and if I write the coordinates of this vector V1 into the column vector, then we can get this matrix P also. Similar for V1, it's A1, A2, A3, and for V2, the coordinates vectors are B1, B2, B3, and this is our second column. Okay, so similarly for V3. So we have got our matrix P, which is our change of basis matrix from S to S dash. Okay, now now suppose that there is a vector V which belongs to our vector space V. This is our vector space. Okay, now this vector V belongs to this vector space V, and V is written as K1 V1 plus K2 V2 plus K3 V3. This is how we are writing V. Okay, this is my V. So what are the coordinates of this V? The coordinate vectors of this V are K1, sorry, yes, K1, K2, K3. And these value of the coordinates of this vector are corresponding to the basis S dash. These are corresponding to the basis S dash. Okay. Now, as we are writing V into the linear combination of this new basis, we can say it as new basis vector in the S dash basis vectors. Okay. Now, if we put the values of the corresponding V1, V2, V3 vectors, which are these, okay, the linear combinations of the UI in the linear combinations of UIs, then we got that V equals to, if I put this value in this equation, then I got V equals to, let's just write it here, K1 bracket A1 U1 plus A2 U2 plus A3 U3 plus K2, and what is our V2? V2 is B1 U1 plus B2 U2 plus B3 U3. These are for our change of basis. Okay, and K3, which is C1 U1 plus C2 U2 plus C3 U3. Okay. Now take out the vector U1 common, U1 U2 U3 common, all these. So by taking U1 common, I got A1 K1 plus B1 K2 plus C1 K3. Okay. And here we'll take out U2 vector common, and we'll got A2 K1 plus B2 K2 plus C2 K3. C2 K3. Let's just write it here. C2 K3. Okay. And taking out U3 vector common, we'll got K1 A3 K1. Okay. K1 A3, same thing. Plus B3 K2 plus C3 K3. Okay, now I have written this vector v in the linear combination of the S basis, which is u1, u2, u2, u1, u2, u3 vector. And this vector, same vector v, here it's in the linear combinations of the v1, v2, v3 vector, which is on the basis S dash, and the corresponding coordinates of this vector v with respect to basis S. These are our basis vectors of S. The coordinates we got here are a1 k1 plus b1 k2 plus c1 k3, and a2 k1 plus b2 k2 plus c2 k3, and our third is a k1 a3 plus b3 k2 plus c3 k3. So from here only you can see that the same vector v which belongs to this vector space V. Okay, now the same vector v has different coordinates of a vector. The same vector v has different coordinates on the basis S and on the basis S dash. On the basis S it has the coordinates like this, and on the basis S dash it has coordinates like this. Okay, now here this is my change of basis matrix from S to S dash. Now if I multiply this matrix with my new basis vector, which is v on the with my this basis, I mean to say that if I multiply this matrix p with the coordinates of the vector v corresponding to basis S dash, let's just write it as that if I multiply p with v of S dash, that is we are writing A1, A2, A3, B1, B2, B3, and C1, C2, C3. And by multiplying this by the corresponding coordinates of the vector V relative to S dash, which is K1, K2, K3, we got the new matrix which is as A1, K1 plus B1, K2 plus C1, K3. Similarly, A2K1 plus B2K2 plus C2K3 and A3K1 plus B3K2 plus C3K3. And what is this? This is my coordinates of the vector relative to the basis S. Okay, relative to the basis S, which is V of S. Okay, so I got that if I multiply matrix of change of basis matrix with the corresponding coordinates of the vector, corresponding coordinates of the vector V relative to basis S dash, I got the coordinates of the vector relative to basis S. Okay, now this is our equation. Okay, now if we multiply P inverse both sides, on multiplying P inverse both sides, we got that V of S dash is equals to P inverse V of S. Now this is the very important result, as it says that we can find the coordinates of the vector V, the coordinates of the vector relative to our new basis, by multiplying the change of basis, by multiplying the inverse of the change of basis matrix from S to S dash and the corresponding coordinates of the vector V relative to basis S. Okay, so this is a very important result. You can write it as, in the theorem you can write it as that let P be the change of basis from S to S dash. Okay, in vector space V, then any vector V which belongs to this vector space. Okay, now any vector V which belongs to this vector space, we can write it as find the so we can find the coordinates of the new coordinates of the vector relative to our new basis, like by multiplying P inverse by the coordinates of the with the coordinates of the old, by multiplying the P inverse by coordinates of the old basis. Okay, so here we are, if we multiply the coordinates of V in basis S by P inverse, we get coordinates of V in S dash to the new basis. Okay, so we don't have to perform that much tantrum that we'll do earlier, that we have to write it in the linear combination, then we'll have to find the value of the constant. We just have to do find the r inverse and multiply the coordinates of, and multiply it by the coordinates of the vector. Okay, now there is another thing, which is there is an important result. There another result, you can write it like this. There is an important theorem which is as that my mapping, I have a linear mapping which is from v1 to v2. Okay, my mapping is going from v1 to v2, and x dash, x and x dash are my basis of vector space v1, and y dash are the basis of vector space v2. Okay, and let a is the matrix of a is the matrix of t with respect to x comma y. Okay, with respect to A is the matrix of T, matrix representation of the transformation with respect to the basis x and y, and B is the matrix of this transformation T with respect to basis x dash and y dash. Okay, and I have the matrix P, which is change of basis matrix, or you can say matrix of transition, change of basis matrix from x to x dash, and there is a matrix Q which is change of basis matrix from y to y dash. Then if we have the situation like this, then we can find B, which is matrix of T with respect to x dash and y dash, by applying Q inverse AP. This is our result by applying Q inverse AP. Let's see that how is this, how we are doing this. Okay, so for this we have to apply the composition. We have to apply the compositions of linear mappings. Okay, so if I have a mapping, we have studied the composition. So if I have a mapping which is going as T U to V, sorry, V to U. Okay, and there is a mapping which is another mapping G which is going on U to W. Okay, then what is this, that I have a mapping which is going from V to U by T and U to W by G. Then the mapping GOT is defined as V to W. Okay, that's how the composition be performed in the linear mappings. Similarly, we'll apply the composition here. So look closely that we have the matrix P, which is our change of basis matrix from x to x dash. Okay, and these x and x dash both belongs to the vector space V1. Okay, so I have the vector spaces V1 and V1. Okay, okay, sorry, V1, as the mapping is going from V1 to V1 uh, for P, and the corresponding basis, change of basis is going from x dash x, and after performing this mapping, okay, that change of basis matrix from change of basis matrix from x to x dash, this is our corresponding P, and the mapping is going from V1 to V1. Okay, because x and x dash both belongs to the vector space V1. Okay, so by this mapping I am getting my P matrix by performing this mapping. Okay, now we'll see what is my matrix A. This is done. What is a matrix A? My matrix A is matrix of the transformation T with respect to x and y, with respect to basis x and y. So I am getting where x is from vector space V1 and y is from vector space V2. Okay, so this transformation is this mapping is performed as V1 to V2. After performing V1 to V2, this is my transformation. Okay, and where x belongs to V1 and y belongs to V2, and after performing this linear mapping I got the matrix A. Okay, and if we looked about the Q matrix, okay, and this is my change of basis matrix from y to y dash. Okay, this is my change of basis matrix from y to y dash, where both the bases are belongs to the vector space V2. Okay, so this is also going from V2 to V2. Okay, where y belongs to vector space V2 and y dash also belongs to the vector space y dash. Okay, now if we look into this one, the P matrix, I have written the change of basis, the mapping here is V1 to V1, where uh, V1 x dash also belongs to V1 and x also belongs to V1. This is my P, and this is the mapping for change of basis matrix from x to x dash. Okay, now if I have to write the mapping for change of basis matrix for y to y dash, what will that be? That will be v2 to v2, for where this is for y dash and this is y. And here I have the mapping which is v2 to v2, and this is my y and this is my y corresponding y dash, which is I have this mapping which is my y dash to y. This is the mapping of y dash to y. Okay, so we have studied that if I have a mapping of x to x dash, x to x dash, which is my P. Okay, then the corresponding change of basis matrix from x dash to x, that will be P inverse. Similarly for y dash, I have a mapping here which is y to y dash, and the matrix corresponds to this is Q, and the change of basis matrix from y dash to y will be Q inverse. Okay, so I have this mapping of Q inverse. Okay, and this is my corresponding composition here. Okay, so these are the mappings that are performed here. We have taken we have taken Q, P and Q into the account. Now we have to find the matrix P, which is the matrix of the mapping P with respect to x dash and y dash. If you look this, that we have performed this, that I have this V1, the I have this V1. Okay, just erase it first. I have this vector space V1, and for B, the mapping, the vectors, the bases are where this belongs to V1 and this belongs to V2. So V1 is the vector space and the basis here is x dash. Okay, and which goes to V2. Okay, and where y dash is my basis for V2. And you can see that the matrix B, we have to find this mapping which is going on V1 to V2 for the basis x dash y dash. This is our matrix B. That matrix B is matrix of T with respect to x dash y dash, and this is how we can represent the linear mapping here. That the matrix B is actually, that's how we can get the our matrix B, which is V1 to V2 with the corresponding basis x dash and y dash. Okay, so this is the mapping here. So, like we have performed here, that if I want to find the mapping directly from V to W directly, then we'll apply the composition GOT. With from that I got V to W. Similarly we'll apply here that my matrix B would be, if we look this, if we multiply this like Q inverse AP, this is my corresponding mapping here, the composition of linear mapping here. Okay, this is Q inverse AP. So B is equals to Q inverse AP, and by applying that, we'll got our matrix on T, which is on V1 to V2. Okay, this is my corresponding mapping, and the result of this mapping I'll got by Q inverse AP. Okay, now we can apply this, see this like this too. Now this is a very important result. Note it. We are going to use it in many things. Okay, so there is an important theorem which is, you can see it on the linear operator. This is my linear operator which is going on v to v. Okay, we have taken here my mapping on two different vector spaces, which is v1 and v2. Let's just consider that if I have a mapping which is on v to v, that is if I have a mapping on linear operator. Okay, that means that, and the corresponding bases are x and x dash, which are basis of this vector space v. Okay, and there is a matrix A which is matrix of t with respect to x basis. Okay, and there is a matrix B which is matrix of t with respect to x dash basis. Okay, and P is the matrix of transition from matrix of transition, or you can say change of basis matrix from x to x dash. This is change of basis. Change of basis from x to x dash. Now I want to find this matrix B. That how can we find this matrix B? So if you B, my B here will be for the linear operator thing when the vector is going to itself. Okay, then the we can write B, we can find B as P inverse AP. Okay, now this can also be seen by the composition of the linear mappings, that if we look to the V part, P part, that the mapping here goes on V to V. Okay, V to V, where the x dash belongs to the vector space V and x belongs to this vector space V. Okay, that's how we define the mapping for change of basis matrix P. Okay, this is the corresponding mapping for change of basis for x to x dash. This is the mapping for x to x dash. Okay, now if we look to the A part, what is A? A is my matrix of T with respect to X basis. So A will be going from vector space V to V, and with respect to X basis, so it will be here X, and there it will be here X. Okay, and similarly, what will be B? So this is from this mapping we'll got our matrix A. Okay, now what is my x dash to x, change of basis from x dash to x? We have seen that if my matrix P is from x to x dash, then the matrix for x dash to x will be P inverse. So, and that also goes from B to B, B to B. Okay, and from x dash. Okay, so the mapping for vector space change of basis matrix for x dash to x will be P inverse. Okay, now we have to find the matrix of T with respect to x dash basis. X dash basis, that is, I have a matrix, I have a vector space V which has x dash, and that is going on vector space V with the which has x dash basis. Okay, so the composition here, you can see that the composition formed with for the mapping, corresponding mapping for the x dash basis here is P inverse AP. P inverse AP. P inverse AP. Okay, and this is my corresponding B matrix. That is matrix of T with respect to x dash basis. Okay, now let's just see it by an example. You'll get a more clarification with this. Okay, so the question here is as that I have a mapping which is r square to r square, and the corresponding mapping is defined as that t of x comma y is equals to 5x minus y comma 2x plus y. Okay, and there are two bases, which is first one is our standard basis e1 e2, and second one is our s basis, which are corresponding vectors are u1 and u2, and the vectors are 1 comma 4 and 2 comma 7. Okay, and I want to find the matrix, find the matrix B that represents T in basis S. Okay, find matrix B that represents T in basis S, and similarly find the matrix A that represents T in basis E. Okay, I have to find these two matrices, and for finding these two matrices, let's just find the matrix A first. Okay, we'll just apply that. So For that, let's just apply the change of basis matrix from E to S. Okay, so what is our change of basis from E to S? Okay, change of basis from E to S. Okay, for that we have known that if I have the change of basis from the standard basis, these E is my standard basis which has vectors as 0 1 1 0 0 1. Okay, as the change of basis is from my standard basis to the basis S. Okay, so the corresponding P matrix will be the corresponding coordinates of this, the coordinates of this vector u1 and u2. If I write this coordinates into my column vector, then I got my P matrix because it is on the standard basis. And we have studied this, that if my matrix is on the standard basis, then the corresponding coordinates of the basis, and if we'll write these coordinates into the column vector, then we'll get a matrix P. Okay, and this will be my change of basis matrix from E to S. So that will be 1 4 and 2 7. Okay, this is my change of basis from E to S. Okay, now if I look to the change of basis matrix A, okay, that represents T in basis E. Okay, in basis E. So what will be my A? My A will be, let's just look at it. So for T of 1 comma 4, T of 1 comma 4, what will that? That will be 1 comma 4, 5 minus 4, that will be 1. Okay, and okay, so sorry, we are finding the matrix A, the with respect to the basis E. I have taken with respect to S. So let's just find the matrix with respect to basis E. So that will be my 1 0 and this is my 0 1. Okay, so for finding this, we'll apply T 1 comma 0. And what will be my T 1 comma 0? 1 comma 0 will be 5 comma 2, and T of 0 comma 1, that will be minus 1 comma 1. And I can write these two vectors uh, in the linear combinations of these standard basis, which is as 5e1 plus 2e2, and similarly minus 1e1 plus e2. Okay, and now if we'll put the coordinates of these vectors, that is 5 2 into the column vector, we'll get our corresponding A matrix. Okay, so my A matrix will be 5 2 and minus 1 1, and hence I got A matrix. Okay, now we'll have to find the matrix B that represents T in basis S. Okay, and for finding that, we'll apply the concept of that B is equals to my corresponding P inverse AP, because here my P is change of basis from East to S. Okay, and I have a matrix A which is my change of which is my matrix A that represents T in basis E. Okay, and I have to find the matrix B that represents T in basis S, and for finding that we'll apply P inverse AP. So for that I have to find the P inverse of P. That will be P inverse is equals to uh, minus 7 minus 1 2 4. Okay, this is my P inverse and this is my A, and here I have P. Okay, so B is equals to P inverse AP, that is equals to minus 7 4 2 minus 7. A is my 5 2 minus 1 1, and P is 1 4 2 7. Okay, let's just multiply that. If we multiply that, it will be minus 35 plus 4, which is minus 31, and it is 7 plus 2, which is 9. Um, okay, and this will be 20 minus 2, which is 18, and this will be I think minus 5. Okay, and we'll multiply this further by the another matrix, which is 1 2 4 7. Okay, and while multiplying by this, we'll got minus 31 minus 46 36, which is 5, and this will be 1, and this will be 18 minus 2 minus 20, and this will be 35 35, this will be 1. Okay, so this is my corresponding B matrix. Okay, so we have finded the matrix B with respect to that represents T in basis S. Okay. Okay. Now this B is equals to P inverse AP. This shows some important results actually. Okay, let's just see them. This shows some similarity. So let's see some similarity here, which are as, let's just consider that I have two matrices, which is A and B. These are my two square matrices. Square matrices. For which there exists an in. So A and B my two are A and B my square matrices for which there exists an invertible matrix. There exists an invertible matrix P such that B is equals to P inverse AP. Okay. Then B is said to be similar to A. Similar to A. Okay. So what we are saying is that we have two matrices, which is A and B my square matrices, and if there exists an invertible matrix P such that B is equals to P inverse AP, then it signifies us that B is said to be similar to A. And what is it means? That similarity, the similarity of matrices is an equivalence relation. Okay, on the square matrices. Okay, so what we are saying that the similarity of matrices, that we are saying that A is similar to B, and this similarity of matrices is an equivalence relation. Let's just see it how. So we have equivalence relation, which is defined as if these three properties are satisfied, where A, B, C, I have three matrices. Okay, and if B is similar equivalence to B. Okay, second, that if B is equivalence to A, then A is equivalence to B. And third property is that if I have B matrix which is equivalence to A and A which is equivalence to C, then I have B which is equivalence to C. Let's just check it by this property. Okay, whether this property is a similarity of the matrices are actually follows equivalence relation or not. Okay, so for checking this, let's just we are checking first condition. For checking our very first condition, that B is equivalence to B, whether it is following here or not. Okay, let's just consider the identity matrix, and we know that the inverse of an identity matrix exists. We'll just study this algebra of matrices later, but for now let's just consider that I am saying that invertible matrix exists for identity. Okay, so identity's inverse exists, that means I inverse is equals to I for identity matrix. Okay, so we can write B as B equals to I inverse BI, and that would be equals to B. Okay, so it is following the property that B is equals to P inverse AP. Okay, and B is equals to I inverse BI. That means B is equivalence to B. Okay. Similarly, for the second, as we are considering that first, if B is equivalent to A, okay, if B is equivalent to A, then it means there exists an invertible matrix P such that B is equals to P inverse AP. Let's just check it, that if B is equivalent to A, then whether A is equivalent to B or not. Okay, then I can write this A as P inverse. How? By multiplying P in this equation, by multiplying P inverse and P inverse A P. Okay, P inverse. Okay, this will be identity. Okay, so P inverse, this is my corresponding A that I got. Okay, now I can write it as P inverse is inverse B P inverse, because P inverse is equals to P. Okay, so this is also following that I have a matrix A which can be written in the let's say q inverse b q, where q is my p inverse. Okay, so it is also following the property where p inverse, here p is inverse is also invertible. Okay, so this can be written in this form too. Okay, so from this we can say that a is also equivalent to b. Now let's check for the third condition. Okay, for checking third condition, we have that we have already said that if a is if b is equivalent to a and a is equivalent to c, then we have a b which is equivalent to c. Okay, for checking third, as b is equivalent to a, then it means that b is equals to p inverse ap. Okay, and as a is equivalent to c, then it means a is equals to q inverse cq. Okay, thus B is equals to what? P inverse AP. And if I put the value of A, which is Q inverse CQ here, then we'll got Q inverse CQP, which is equals to, I can write it as P inverse Q inverse CQP, which is equals to QP's inverse, because QP's inverse is equals to P inverse Q inverse. Okay, we'll study this property in the inverse and see QP. As we know that QP is invertible, so from this we got that A is equivalent to C. So it is satisfying the properties of equivalence relation. So from this we got that similarity of matrices are equivalence relation. Okay, and from this, why are we reading about this? The main theorem from this we got that two matrices two matrices represent two matrices represents the same linear operator if matrices are similar. Okay, so two matrices, there are two matrices, they would represent the same linear operator. They would represent the same linear operator if these matrices are similar, because it means that all the matrix representation of linear operator T form an equivalence class of similar matrices. Okay, so from this we got that all the matrix representation, all the matrix representation of linear operator T form an equivalence class, equivalence class of similar matrices, similar matrices. But here is one thing which is we are talking about on the linear operator, on the linear operator, which is as T v2 v, not on the general vector spaces. Okay, we are talking about the linear operator where I have two matrices, they would represent the same linear operator if the matrices are similar. Okay, now a linear operator T. Okay, this, let's say I have this linear operator T, then this linear operator was said to be diagonalizable. This linear operator would said to be diagonalizable if I have a basis S. If I have a basis S of the vector space V, such that T is represented by, if T can be represented by a diagonal matrix. Okay, what we are saying that the linear operator T, this is my linear operator T. The linear operator T would said to be diagonalizable if there exists a basis S of the vector space V. Okay, where T is going from V to V. Okay, so there exists a basis S of this vector space V such that T is a diagonal matrix. If the matrix representation of T with respect to the basis S is my diagonal matrix, then we say that my T is diagonalizable. Okay, now when would be the case that we can say that my T is diagonalizable? It is not always the case that T always forms the diagonalizable diagonal matrix. Okay, this will only be possible if there exists an, so this will only be possible if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. Okay, diagonal matrix. So we can write it as like that. Let A be the matrix representation. Let A be the matrix representation of linear operator T. Okay, then T is diagonalizable. Diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. Diagonal matrix. This is the only case when we say that my mapping is diagonalizable, that the T is diagonalizable, that linear operator is diagonalizable. From this, what we are mean to say that T is diagonalizable if and only if its matrix representation can be diagonalized by similarity transformation. Okay. Okay. Now, if let's just look at it by an example, that I have a linear operator which is T. Okay. I have this linear operator and E and S are my corresponding bases of vector space R square. Okay, this is going on R square to R square. Okay, and the transformation T of x comma y is defined as 2x plus 3y, 4x minus 5y. Okay, where E is my E1, E2 and S are 1, 2 and 2, 5. Okay. Now what will be my matrix A relative to basis E? That would be 2, 4, 3 minus 5. Okay, we just have to write the coordinates of this because if you try to find out, that would be this only. Okay, because it's on the uh, relative to the standard basis, we can write it to the coordinate only. Okay, because that would give us this only. Okay, so this will be my A. This is the matrix relative to the E. Okay, now if we'll just find the matrix B, which is on the basis S. Okay, what will be my matrix B? My matrix would be T of 1 comma 2, which is equals to 8 minus 6. Okay, and T of 2 comma 5, that would be what is this? That will be 19 and it would be minus 17. Okay, now we'll just write this into the linear combinations of this S vector, which is x1 1 comma 2 plus y1 2 comma 5 and x2 uh, this would be 1 comma 2 plus y2 2 comma 5. Now find the values of these constants a1, x1 y1 x2 y2. You can also do this by you can also find the matrix B by applying P inverse AP. Okay, you can also do by that in that way, but let's just do it like this. Okay, so my x1 plus 2 y1 plus equals to 8. This is my first equation. Second is 2x1 plus 5y1 equals to minus 6, and I can write it as multiplying by 2, 2, 4, 8 to just 16, and minus minus minus, that would be minus of y1 equals to 22. So y1 is equals to minus of 22, and similarly I got my x1 as 8, and this would be 8, this is 2, 8 plus and 22 into 2, which is 44. Okay, so I got x1 is equals to 52, y1 is equals to minus 22. Okay, now let's just solve another equations, which are as x2 plus 2y2 is equals to 19 and 2x2 plus 5y2 equals to minus 17. Okay, multiply this by 2, which is 2, 4 and 2 to 38, and that would be minus minus minus, this will be cut, and minus of y2 equals to, that would be this would be plus 55. So y2 is equals to minus of 55, and x2 would be if you apply this, that would be x2 is equals to 19, and here it is 55 plus 110 and x2 would be 129. Okay, so this is what I got. I can write it in the linear combination like this. I got my coordinates, which is as I can write it as 52u1 plus, sorry, minus 22u2, and this in the 129u1 minus 55u2, and my corresponding B matrix would be 52 minus 22, 129 and minus 55. Okay, so I got my A matrix and my B matrix. Okay, now if we find the trace and determinant of these two matrix, what will be my trace and determinant? Okay, so if I find the trace of A, what is trace of A? Trace of A is the sum of elements of the diagonal, sum of the diagonal elements, that would be minus 3 here. And if I find trace of B, that would be minus 3. So these matrix, these A matrix and B matrix are on the two different bases. A is on relative to E and B is matrix is on relative to basis S, but you can see that they have same trace. Okay, and if I find the corresponding determinants of this, determinant of A and determinant of B, that would also be same, because the the transformation here follows a very important property, that that is that property is said to be let's say name is as functions and similar matrices. There is a very important concept that why my two matrices which are on different bases gives me the same trace and same diagonal, same determinant, because let's say if I have is a f is my function, f is a function on square matrices, on square matrices. Okay, and this f is that assigns the same value to similar matrices. Okay, this function f assigns same value to similar matrix, that is fa is equals to fb, where a is similar to b. I have these two matrices where a is similar to b, and here f is the function which is on the square matrices, and this function assigns the same value to the similar matrices, that is fa is equals to fb. Then f induces a function on linear operator t as that f of t is equals to f of ts. F of t is equals to f of ts. That means this is the case. That means that the function on the linear operator t, the function on the linear operator t is equals to the function on the linear operator t with respect to any basis. That means let's say that's what the case here, that I have the matrix A which is respect to E, and I have the matrix B which is on the basis S, and these two matrices have same value of the function which is trace, and these both have same value of the function trace which is minus 3. Okay, and this is due to this property that which is of functions and matrices, that is if I have a function on the square matrices which assigns the same value to the similar matrices, that is f equals to fb, then this function induces a very important function which is on the linear operator t, which is on the linear operator. It should be note that it is on the linear operator. It is on the linear operator. Okay, that means f of t is equals to f of t of s, and the function, there are many functions which comes under this, like if I the matrix a, there is a many matrices, like there are many bases. Okay, there is a matrix. Okay, let's see it like this, that I have this transformation t. Okay, linear operator t. Okay, and I have the corresponding matrix a which is on the basis S, and another matrix B which is on the basis S dash, and another matrix C which is on the basis S dash dash, and another which is on D and on the basis S dash dash dash. Then the corresponding trace, the corresponding functions which are trace determinant examples. These are, I am taking these as an example, that traces and determinants of these functions are all same. Okay, it doesn't matter that what is the basis of these matrices, but their functions will always be the same. Okay, because they follows the properties of similarity. Okay. Okay, now uh, let's just do an example, which is of, we have done an previously an example of counterclockwise. Okay, in that case, let's just say that I have, suppose I have x axis and y axis. I have these two axes in plane r square, and these are rotated rotated counterclockwise counterclockwise 45-degree, so that new new x dash axis and y dash axis are along line y equals to x and y equals to minus x respectively. And I have want to find the change of basis matrix P. Change of basis matrix P. Okay. P. So the case here is that we have the, this is our x-axis and this is our y-axis. Okay, this is in r square plane. Okay, and we have rotated these x-axis and y-axis in the counterclockwise direction by 45-degree. Okay, and that our new axes are on the line y equals to x and y equals to minus x. Okay, and what is my line y equals to x? This is my y equals to x, and this is my line y equals to minus x. Okay, in these, along these lines we have changed our axis, so that would be my x dash axis and this is my y dash axis, and this is making the angle 45-degree. We have moved this into the counterclockwise direction. Okay, now what is my rotation matrix? My rotation matrix is cos theta minus sin theta cos theta. Okay, this is the rotation matrix. Okay, and as it is about angle 45-degree, then it will be cos 45-degree minus sin 45-degree, sin 45 cos 45. Okay, and what are the corresponding values with this angle? With these angle, cos 45 would be 1 by root 2, and similarly minus sin 45 will be minus 1 by root 2, and this is 1 by root 2, and this is also 1 by root 2. Okay, and for finding, we have to find the change of basis matrix P. Okay, now for that, the unit vectors in the direction of new x dash and y dash axis, what are these? Now these we find the unit vectors as v dash, this is a vector v, we have to convert this vector into the unit vector, then we'll just divide the vector by its norm. Okay, by its norm. So here our unit vectors are, because on in the direction of x dash and y dash axis are u1 1 by root 2 and 1 by root 2. Similarly, u2 are minus 1 by root 2 and 1 by root 2 by this. Okay, as the norm of these are 1, so these are already the unit vector. Okay, now the unit vectors in the direction of the original x and y are on the usual basis. That means on the standard basis of r square. That is on 1 comma 0 and 0 comma 1. Okay, so as these are on the standard basis of r cube, so we can write the coordinates of u1 and u2 in the column form. Okay, then we will get a change of basis matrix, because the previous x axis and y axis are on the standard basis, that is usual basis. Okay, so we don't have to perform all that things, we just have to write the coordinates of u1 u2 in the column vectors, that will be 1 by root 2 1 by root 2, and this would be minus 1 by root 2 1 by root 2, and this is my corresponding change of basis matrix for the new axes, which are y dash and x dash. Okay, now there is one point to note here is that this is my rotation matrix. Rotation matrix when the rotation is in the counterclockwise direction. Okay, and the matrix changes, which is for clockwise direction, for clockwise rotation. If the rotation goes in clockwise direction, then my matrix would be cos theta, sin theta, minus sin theta, and cos theta. For clockwise rotation, the matrix would be like this, and for counterclockwise, it would be like this. Okay, so this is all about the change of basis matrix. Okay, thank you.